Let us start. Let us finish the last problem of the chapter on psychometry. What we have decided in the discussed in the last class, the phenomenal, just a second. The phenomenon of adiabatic mixing of two streams. Where we consider two streams of air, 1 and 2, mixing adiabatically as given in the figure, first figure here. Here, where the two air streams, 1 and 2, mixing adiabatically, where stream number one has the M1 is the mass of the air entering at point 1, H1 enthalpy of the entering air at point 1, and W1 specific humidity of air entering at 1, means the entrance at 1. And there is another entrance at 2, and M2, H3, and W2 correspondingly is the value of air entering at 2. And both these entering air are mixed and leaving this mixing system, and thus mixing of the mass, enthalpy, and specific humidity of the mixture is M3, H3, and W3. We have discussed that for the mass balance, as there is, we are supposed to be understood that there is no loss of enthalpy, no loss of specific humidity, and no loss of any quantity of the air. So we have for the mass balance, M1 and M2, the mass of the air entering at 1.1 and 1.2 is equal to the mass of the air exiting at 2.3. The energy balance, mass multiplied by the enthalpy of the incoming air per kg, plus mass multiplied by the enthalpy of the incoming air through port 2 per kg is equal to mass of the total mixture multiplied by the enthalpy of the mixture of air. So the mass balance for the water vapor also, the specific humidity means amount of water dissolved in kg per kg of the air vapor mixture multiplied by the mass of the air entering is the entering from through port 1 and that 2 plus 2 mixed together, get the M3 and W3, the specific humidity of the mixture of air multiplied by the mass of the mixture of air. So this is the mass balance of water vapor, energy balance, mass balance, and only mass balance. So after substituting value of M3, eliminating M3, we'll get M1 plus M2 is equal to H3 by H2 divided by H1 minus H3, means enthalpy of the outgoing mixture minus enthalpy through port 2 minus divided by enthalpy of the port 1 minus enthalpy of the outgoing mixture. That is the ratio of the mass of the air coming through port 1 and divided by mass of the air coming through port 2. Similarly, the substituting the values of M3, will also in equation 3 we'll get M1 plus M2, W3 minus W2, W1 minus W3. And from the equations, both of these equations, we get the mass balance, the ratio of the masses of incoming air in both the two ports, so M1 and M2 is equal to the ratio of the difference in enthalpy from the two process, from the outgoing air to the entering air through the point 1 and 2, and H1 minus H2 is the outgoing of the entering air through point 1. So W23 minus W2 is going to just same for specific humidity of the mixture of the entering air of point through point 2 and the entering air at point 1 and the mixture. Now let us go through the last remaining problem of this chapter. That is problem number 30. 800 cubic meter per minute of recirculated air at 22 degrees centigrade dry bulb temperature and 10 degrees centigrade dew point temperature is to be mixed with 300 cubic meter per minute of fresh air at 30 degrees centigrade dry bulb temperature and 50% relative humidity. At 30% dry bulb temperature, 50% relative humidity. Determine the enthalpy, specific volume, humidity ratio, and dew point temperature of the mixture. What is given? Both this incoming air, the mass flow in volume of the volume, not mass flow, but volume of the flow of the volume of M1 and the mixture number 1 and mixture number 2 is given with their dry bulb temperature, and for one case the dew point temperature and another case relative humidity. Now we have to find out the hazard ratio. So what is given is the volume 800% recirculated air, that is 300 cubic meter per minute, and TD2 is the temperature of the dry bulb at the emission number 2, and 10 degrees TDP is the 10 degree dew point temperature of the dry bulb 2. Similarly, same is the case with V1, the mixture of air through source 1 and source temperature of the dry bulb air and system and the relative humidity. Just a second. Now, the condition of the what you got here, this is a psychrometric chart we have here. The condition of the recirculated at 22 degree by center, that is at point 2 at 22 degrees centigrade and 10 degrees centigrade dew point temperature. If the dew point temperature is on the dew point line, we find that line and draw a horizontal line, and while we find plotted the 22 degree centigrade temperature and draw a vertical line which mark together to form the point 1, point 2. Now let H2 is the point 2, then H3, the enthalpy of the mixture here, which is supposed to be in between the point 1 and point 2, because the enthalpy will be more at the midway or in between H1 and H2. The point 2, and now what the point condition of fresh air, 30 degree dry bulb temperature and 50% relativity at point 1. So what is 30 degrees centigrade we have brought here, and we find out the 50% relative line, and we draw a vertical from 30 degrees centigrade to up to that line, and the point of position will be point 1. And next we joined the point 1 and 2. Now from the psychrometric chart, if we drop a vertical on the enthalpy line from 1 and then from 2, it will 1 and from 2, then we'll find from the enthalpy chart that H1 64.6 kilojoule per kg and H2 41.8 kilojoule per kg. The specific humidity at point 1, if we have to draw a vertical horizontal 1 to 2, from 1 to up to the specific humidity line, and 2 to up to the specific humidity line. So we'll get the from 0.1 0.134 kg per kg of dry air, 0.0076 kg per kg of dry air. So, now specific humidity at 0.2. Okay. Now specific volume, that's also available from the psychrometric chart. That is VS1 0.876 cubic meter per kg, and that of 0.2, that is also 0.846 cubic meter per kg of dry air. Now, the mass of the fresh air at 1 is the volume of the air coming divided by the specific volume. Specific volume, it will become 300 divided by 0.876 as V1. The volume of the moving air coming in is given and 342.5 kg per meter per minute. Similarly, V2 is the volume of the tube, V2 divided by VS2. V2 is given as 800 cubic meter per kg, and VS2 is given as from the psychrometric chart 0.846 kg per cubic meter. So this becomes 945.6 kg per meter square. So we've got M1 and M2. Thus, we can use this equation M1 by M2 is equal to H1 by H1, H3 minus H2, H1 minus H3, where we know what is H1 and what is H2, and M1 and M2, but we don't know the value of H3. So putting the known values of M1, M2, H1, H2, and unknown values of H3, then and simplify, we get H3 is equal to 4.86 kilojoule per kg of dry air. This is one of the answer. The specific volume. The specific volume at 0.3 and on the line joining 1 and 2 corresponding to enthalpy H3. From 0.3, the specific volume of the mixture at 0.3 can be drawn horizontal line up to the specific volume line, which will give us the specific volume of the mixture 0.85 cubic meter per kg, and humidity ratio is the of the mixture is W3, or humidity ratio or specific humidity is W3.0092 kg per meter. That's also available from the 0.3. And dew point mixture at 0.3, if we draw the horizontal line up to the dew point temperature, it will get 0.TDP3. It is 13 degrees centigrade. Next, the last problem. The saturated air leaving the cooling system leaving the cooling system of the saturated air leaving the cooling section of an air conditioning system at 14 degrees centigrade at the rate of 15%. At the rate of 14 degrees centigrade at the rate of 50 kilometer. The saturated leaving the cooling section means of an air conditioning system at 14 degrees centigrade at the rate of 50 cubic meter is mixed adiabatically with the outside air 30 degrees centigrade, which is at 30 degrees centigrade and 60 degrees centigrade. 60% relative humidity at a rate of 20 cubic meter per minute. Assuming the mixing process occurs at pressure of 1 atmosphere, therefore determine the specific humidity, relative humidity, trival temperature, and volume flow rate of the mixture. So we are having two flow of air. One is saturated, leaving the cooling section of air conditioning system. Its temperature is TD2. Its trival temperature is 14 degrees centigrade, and rate of the volume of the air coming in inside is equal to 50 cubic meter per minute. And similarly, we have another mixture that is outside air or atmospheric air, which is at at atmospheric pressure, at 1 atmospheric pressure, means that equal to the, not at pressure, but equal to the atmospheric pressure. Its at divergent temperature is 32 degrees centigrade, and phi 1, the relative humidity, means the amount of moisture presence in the air vapor mixture, and to the ratio of the amount of moisture present in the vapor mixture to the amount of moisture when the air is fully supported, that is the 60% of the fully supported mixture. So this air contains only 60% of the saturated, 60% of the air vapor than that of the saturated mixture. So phi 1 is there, and V1 is 20 cubic meter per minute, and atmospheric pressure is given as 1 atmosphere. So in the psychrometric chart, we have to plot the respective temperatures. The condition of saturated air at dry-bulb temperature is 14 degrees centigrade. We plot it here on the dry-bulb temperature line at point 2, and draw a vertical on the saturated up to the saturated curve. Now, because it is told that it is the saturated air, so the wet bulb temperature will be equal to the saturated temperature. So that is equal to 0.2 will be the on the right, lies on the saturated vapor line, saturated vapor curve. Next, the outside air temperature, dry-bulb temperature is 32% here, 32 degrees centigrade here, and it has a relative humidity 60%, which we have to find the relative humidity line equal to 60% and draw a vertical from 32 to up to the 60% relativity line, which is at, we will give you the 0.1. Then join the 0.2 and 0.1 and 0.3, the mixture point will be in between them. Now we know from the psychrometric chart, if we drop the enthalpy and drop a vertical from 0.1 to the enthalpy chart, we'll get H1, which is equal to 78 kilojoule per kg. Similarly, from 0.2, if we drop it on the enthalpy chart, you'll get the enthalpy of the mixture 2, which is 39.4 kilojoule per kg. And specific volume, if we drop a horizontal up to the specific volume line from on the psychrometric chart, we'll get VS1 0.089 kilometer per kg of dry air, and VS2 0.826 millimeter per kg of dry air. So specific volume is available, specific volumes of both the mixture available, and we don't know what is the specific enthalpy of the mixture after mixing up to the 0.3. We know the mass of the outside air at 0.1 is mass divided by the volume of the incoming air divided by specific volume of the incoming air. Both are available as 20 for the volume of incoming air per cubic meter per minute, and specific volume means 0.889 kg per cubic meter of incoming air, that is equal to 22. If the ratio will be equal to 22.5 kg per minute. And similarly, the mass of the saturated incoming air leaving the cooling section is equal to M2, the volume of the outgoing air, which is given as 50 cubic meter per minute, and specific volume of the outgoing air of incoming air, that is given as 0.826 kg per cubic meter. So the ratio will be 60.53 kg per minute. So we now have this ratio equation M1 by M2, H3 minus H2, H1 minus H3, where M1, M2, H2, H1 is known, only H3 is unknown. We put the known values and to calculate the unknown value of H3, which is equal to 49.86 kilojoule per kg of dry air. To find the specific and relative humidity, so we plot the 0.3 on the line joining the points and 2 corresponding to enthalpy 3. If we drop a particle on the line 1, 2 from the enthalpy H3 is equal to 49.86 kilojoule per kg, we'll get the 0.3 on the line. Then from the 0.3 on the psychrometric line, we draw a horizontal line intersecting the specific humidity line, which will give us a specific humidity line which will give us the specific humidity at 0.3, 0.0122 kg per kg of dry air, and the relative humidity of the mixture with that 0.3 will given by the curve of the relative humidity, which is closest to the 0.3, which will be around 90%. And dry bulb temperature of the mixture 0.3 feet off a vertical to the dry bulb temperature line. It will intersect dry bulb temperature line at 90 degrees centigrade, giving the dry bulb temperature of the mixture. Now, the volume flow rate of the mixture, that is M3. From the cyclometric chart, we have the specific volume of the mixture as 0.483, and volume flow rate of the mixture will be V3 multiplied by M1 plus M2. The mass of the incoming air are 1 and 2. Both the mass will be added together and multiplied by the specific volume of the mixture. You will get the volume flow rate of the mixture coming out at 0.3, that is 70 cubic meter per minute. So with this, we are finishing our chapter on psychometry. Next, we'll go for our next and last chapter of our module, that is comfort condition. Now, strictly speaking, the human comfort depends on psychological and physiological and psychological condition, such as it is difficult to define the term human comfort. There are many definitions given for different bodies, but the most accepted definition from the subject point of view is given as the American Society of Heating, Refrigeration and Air Conditioning Engineers, ASHRAE, which states human condition comfort at that condition of mind which expresses satisfaction with the thermal contact environment. Is that condition of mind which expresses satisfaction with the thermal environment. So it is that you are comfortable when you are satisfied with the thermal environment. Your means your surroundings temperature, humidity, etc. When you are satisfied, then you say that it is you are comfortable and it is a human comfort. The thermal exchanges of body with the environment. The human body, thermal exchanges of body with the environment. The human body works best at certain temperature like other machines. At certain temperature like other machines. It is not comfortable also, which means it's not comfortable for all temperatures. But it cannot tolerate wide range of variation in their environmental conditions like machines. So we cannot tolerate a lot of variation in their environmental temperatures. The human body maintains a thermal equilibrium with the environment by means of three modes of heat transfer: evaporation, radiation, convection. So all three modes of heat transfer is required for the human body to make the thermal equilibrium with the surroundings environment. The conduction, convection, radiation. The way in which individual's body maintains itself a comfortable equilibrium will be its automatic use of now, the human body works at a certain temperature like any other machine. Well, the way in which individual maintains itself in comfortable condition will be its automatical use of one or more of three modes of heat transfer. Automatic use. So, human body feels comfortable. The heat produced by metabolism of the body is equal to the sum of the heat dissipated to the surroundings, and the heat stored in the human body is raised by raising the temperature of body tissues. So the comfort condition depends when all the human body is comfortable, when the heat produced by the human body by the metabolism equal to the heat dissipated to the surroundings and the heat stored in the human body by the rising of the body issue. So both these things are important. The amount of heat you are dissipating the surrounding, as well as amount of heat we are holding in the body, and is supposed to be equal to the amount of heat we are producing by the metabolism of the body. This phenomenon will have the following equation, and it's given: metabolic heat produced for the body useful rate of working, minus useful rate of working, and QM minus W is supposed to be heat dissipated to the atmosphere, which is equal to heat lost by evaporation, heat lost or gained by radiation, heat lost or gained by convection, and heat lost stored in the body. So that is evaporation, loss or gain plus minus. That's why by radiation, loss or gain plus minus by convection, and lot of heat stored in the body. It may be noticed that the metabolic heat produced QM depends on the rate of food energy consumption in the body. As a result, weak or sick man will have less metabolic heat production. The heat loss by evaporation is always positive. It depends on the vapor pressure difference between the skin surface and the surrounding air. The heat loss in evaporation is always positive. Depends on the vapor pressure difference between the skin surface and the surrounding air. The metabolic heat, what is giving that, depends on the rate of food energy consumption. At fast, weak and sick man at fasting will produce late metabolic heat. So the amount of food which we are consuming and the food energy we are consuming will produce the same amount of heat in the metabolism. So the heat loss, now evaporation will become heat loss by the evaporation is always positive, means by evaporation of on the surface of the body will always lose. It depends on the vapor pressure difference between the skin surface and surrounding difference there. The heat loss of evaporation is given by QE CD multiplied by A, PS minus PV, H, FG into CC, where CD diffusion coefficient in kg of air evaporated per unit surface area and pressure difference per hour. And A, skin surface area 1.8 meters square for normal man, plus multiplied by saturation vapor pressure corresponding to skin temperature, and vapor pressure of surrounding minus vapor pressure of the surrounding air. Saturation vapor minus vapor pressure of surrounding air multiplied by the latent heat of vaporization, that is 2450 kilojoule per kg. And the CC factor, which accounts for clothing warmth. So there are two factors: diffusion coefficient and factor for the clothing warmth, and it is to the skin surface, which is supposed to be 1.8 meters square for normal man, and multiplied by the saturation vapor pressure corresponding to steam temperature. So steam temperature, you have to find out from the steam table what is the saturated vapor pressure. Then PV, vapor pressure of surrounding air, vapor pressure and latent heat of vaporization 4450 kg per kg. The value of QE becomes 0 when QE will become 0, then when the surrounding air temperature is equal to the skin temperature, they are saturated, or when it is higher than the skin temperature, there is nearly saturated. So what is going on here? That is the saturation vapor pressure, steam temperature, and vapor pressure of surrounding air. If the vapor pressure corresponding to steam temperature, and that is equal to the vapor pressure of the surrounding air, what we found, and air is fully saturated, and when this is higher than skin temperature, there is nearly saturated. If it is nearly saturated also, we more or less remains same. Now, the plus sign is used when the heat is lost to the surrounding, a negative sign is used when it is absorbed from the surroundings. The plus sign used temperature of the body raised, and negative sign is the temperature of the body fades. The value of QE is never negative when saturated pressure of the body, saturation pressure PS is less than PV. Where PS is the skin saturated vapor pressure transferred to skin temperature, PV vapor pressure of the surrounding air. So saturated vapor pressure corresponding to skin temperature is less than saturated vapor pressure of the surrounding. Then Q will be negative, negative. The skin will not absorb moisture from the surrounding air as it is a fully saturated place. Because we are seeing it may be less or more than the surrounding vapor, but it is fully saturated. Means we cannot absorb anything from the surroundings. The only way for equalizing the pressure difference is by increasing PS to PV by rise of the skin temperature from the sensible heat flow from air to skin. The heat loss or gain to the heat loss or gain by radiation from the body to the surrounding depends on the mean radiant temperature. Heat loss or gain by radiation from the body to the surroundings depends on the mean radiant temperature. It is the average surface temperature of the surrounding objects when properly weighted. The heat, how much amount of heat or is we are gained by radiation from the body to the surrounding, either lost or by gain from the depends on the mean radiant temperature. It is the average surface temperature of the surrounding objects when properly weighted. Average surface temperature, and when properly weighted, it varies from place to place inside the room. So, if you are inside the room, there are so many different furnitures are present in the room, and they also have a certain temperature and then serve of their surface, and we should have to find out the average surface temperature of all them of them. And it varies from place to place. It's also may not be same everywhere, but that's why you are taking the average, and it varies from place to place. When the mean radiant temperature is lower than that, when this mean radiant temperature is lower than the dry bulb temperature of the air in the room, then Q bar will be positive. That is, body will undergo a radiant heat loss. Means dry bulb temperature of the inside room is higher than the radiant temperature of the mean radiant temperature of the surroundings. Thus, the Q bar is positive always, and that is body will undergo the radiant heat loss. On the other hand, because your surroundings furnitures have of lower temperature, and you will lose certain amount of heat from your body to maintain the temperature of the surroundings. On the other hand, the mean radiant temperature is higher than the dry bulb temperature. Q bar is negative, body will under radiant heat gain. So, if the surroundings temperature is high than your body, or because your body more or less follow the temperature of its surrounding atmosphere, it will absorb more than those. It will absorb more heat from the surroundings, furnitures, and other objects. That is, the body will undergo radiant heat gain. So this is shown here. Heat from the future, from the flue gases is coming out from everywhere, and heat coming out. This is a boiler or some heated furnace or something. The heat is coming out from the stone, and that is radiating heat from the surroundings, and the heat through the skin of the boiler, even though it is extremely well insulated, but heat will come up to a certain extent from the skin of the boiler. And also there is a relief valve. If the relief valve is open to relieve the pressure to a certain extent, then it's also dissipate heat or radiate heat to the surroundings. The heat system to the building radiators. So the heat system to the building radiators, it is the goes the building radiators. So this also have some sim. The heat through the skin of the boiler and condensate liquid return. The condensate of the liquid will return from here. Say 22.8 degrees centigrade, 50% humidity, and the 37 degrees centigrade heat flowing from body to ambient temperature at just the right rate. Because your body temperature is not less or more, and your starting temperature is more or less the right temperature. Here, what we see, the boiler can be compared to the inner body in that it uses for the fuel or energy. Then the ambient temperature is 38.8 degrees centigrade, body 30 near less equal to 30 centimeter. The human body must give up some of its generated heat to the surroundings. So because it is more or less same. Heat loss by the convection is given here. It is given here, and heat loss by radiation also given here. The heat loss, water vapor precipitation means the amount of sweating you are doing on the operation of the by the respiration. The three direct way of human body gives of heat: conduction, convection, and radiation. This is conduction. This is heat loss by conduction from surroundings, heat loss by convection, and heat loss by radiation here. The heat loss by convection, QC, from the body the surrounding is given by QC is equal to U into A. U stands for body's film coefficient of heat transfer, and A, the body surface area, 1.8 cubic meter for normal man, and TB, temperature of the body and temperature of the surroundings. When the temperature of the surrounding is higher than the temperature of the body, when the temperature of the body of the surroundings is higher than the temperature of the body TB, and then QC will be negative, means heat transferred by convection is more, the heat will be gained by the body. Heat transferred by the convection, body will gain heat. It is negative, means convection from the surrounding is losing some of the heat, whatever is small, it is obtained from the surroundings. On the other hand, if the temperature of the surrounding is less than the temperature of the body, Q will be positive, then heat will be lost by the body and surrounding will be gained by the heat of the body. Since the body film coefficient ways of heat transfer increases with the increase in air velocity, therefore higher air velocities are produced are comfortable when body heat film coefficient of heat transfer increases with the increase in air velocity. So higher the air velocities will produce uncomfortable, will produce uncomfort when TS is higher than TB. The higher velocities are recommended when TS is lower than TB. When T is equal to Q1 and TC are high and positive, TE bands. When QE, Q1 and QC, when conduction, radiation, and conduction, radiation, TV is the TE is the evaporation. Yes. When the heat caused or gained by evaporation, radiation, and conduction are high and positive, then QB plus Q1 and QC is greater than QM minus W. Then the heat stored in the body, QS, will be negative. That is, the body temperature falls down. The body will release heat to maintain the heat balance. Thus, a sick, weak, and old, and a fasting man really feels more cold. On the other hand, gets fever when high internal body activities increases to such an extent that high internal body activity increases to certain extent that QS become positive for the given QB, Q1, and QC. So these are the important things: the heat gained by evaporation, heat gained or loss by radiation, heat gained by convection, means heat gain here. Evaporation by conduction, radiation. Conduction and radiation. When the state stored in the body are high and positive, and with all these things, three type of heat: conduction, convection, and evaporation are high and positive, and QV, Q1, and QC are greater than, and that is Q1, QC, and QC, the addition of all of them, and greater than Q1 minus W, means the amount of heat produced by the metabolism minus the amount of work done. Then the heat stored in the body will negative, means the body temperature falls down. is greater than that. When the amount of heat we are produced is greater than this, then it requires more heat in this direction. So the more heat due to evaporation, loss, heat addition, heat, and so the body temperature starts falling down. Thus, the sick, weak, and fasting man feels more cold. On the other hand, a man's fever with high internal body activities increases QM to a certain extent that QS become positive. QV increases QM to such extent that QS become positive for the given QV, QR, and QC. The heat stored in the body has maximum and minimum limits, which, when exceeded, has maximum and minimum limit when exceeded brings death. The usual body temperature for normal men when QS is equal to 0, usual body temperature is 37 degrees centigrade or 98.6 degree Fahrenheit or 37 degrees centigrade. The temperature of the body when falls below 36.5, 98.7 and exceed 40 degrees centigrade is dangerous. This is 105 degrees Fahrenheit. Means less than 98 degrees Fahrenheit and more than 105 degrees Fahrenheit is dangerous. There is some kind of thermostatic control called vasometer control mechanism in the human body, which maintains the temperature of this is called vasometer control mechanism, vasometer control mechanism. A vasometer control mechanism in the human body, which maintains the temperature of the body at the normal level at 37 degrees centigrade by regulating the blood supply to the skin. When the temperature of the body falls, that is the heat stored QS in the body is negative. When the vasometer control decreases the circulation of blood, which decreases conductivity of nerve cells, decreases conductivity of nerve cells and other tissues with the skin and the inner body cells. This allows the skin temperature to fall below, allows higher internal temperature of the body cells beneath. When the temperature of the body rises, that is the heat stored QS in the body is positive, then the vasometer control increases the blood circulation, which increases the conductivity of tissues and hence allows less temperature drop between the skin and internal bodies. So what you see, then it's important that heat loss due to radiation, heat loss due to radiation, evaporation, and conduction. And so all of them are positive, means you are losing it and you are gaining it and are greater than QL by W, means the heat gained by the mechanism minus the amount of work you have done, means amount of work is stayed in the body, and which is amount of this fall is heat lost and radiation, conduction, convection like this, which is heat lost. So all this heat lost, radiation, convection, and radiation, there is more and negative. When all this heat lost are more than the metabolism of the body we are producing minus the work we are doing it, then this is negative, then the heat stored in the body will be negative, means the heat will be, that is the body temperature, or strength with the body will be negative. So the body temperature will comes down. So if so many heat has been lost, means lost to the surroundings and it's greater than the temperature of the body, temperature, the heat produced in the body, means all this body stored, heat stored in the body will be negative because it has to supply the heat loss to the surroundings. So the body temperature will start falling because it is losing a lot of energy or temperature into the surroundings. Thus, sick, weak, or man feels more cold because his temperature is high and it's supposed to lose much more heat to the surroundings than a fully fit and healthy man. A man gets fever when high internal body activities increases QM, so that to some extent that QS become positive for the given QR, QC and QC. So if the body temperature is less than the fever with high internal body fever activity started to such an extent that QS become positive, means more temperature is being absorbed, that is being built by QR, QC and QR, QV and QC. The heat absorbed in the body has maximum and minimum limits. So, which is given as 37 degree for the maximum, and minimum is the 37. It is 37 or degrees centigrade, or 19.6 degree Fahrenheit is the maximum, minimum, and maximum is 105 degree Fahrenheit or 40 degrees centigrade. So, if the normal man has temperature falls below the minimum and or exceeds the maximum, it is dangerous to the human being. So there must some kind of thermostatic control or the vasometer control mechanism. Vasometer control mechanism in the human body, which maintains the temperature of the body at the normal level of 37 degrees centigrade. And there is a control system which maintains the control in the body, which maintains the body around 37 degrees centigrade. So, say, by regulating blood supply, everything. When temperature of the body falls, then the vasometer controls decrease the circulation, we decrease the conductivity of nerves and other issues. This allows skin temperature to fall, but allow higher amount of internal temperature of the body, cells spinning. Internal temperature high, but skin temperature is less. When body of the body rises, then the vasometer control increases the blood supply, which increases the conductivity of the tissues. Hence, less temperature is dropped within skin and enough body cells. The human body feels comfortable when there is no heat in the body because of temperature. When heat stored in his body is zero, any variation in body temperature will act as a stress to the brain, which ultimately results in